The talk tonight is fully anhydrous HCl electrolysis with polybenzimidazole or PBI membranes. I'm Dr. Ben Meekins, Research Assistant Professor, Department of Chemical Engineering, Assistant Director at the Hydrogen and Fuel Cell Center. And this work was largely conducted in the Hydrogen and Fuel Cell Center, but I'll talk a little bit about some of the additional work. I do think this work is really cool. It opens up some really interesting possibilities for electrochemistry. Kind of delve into that as the time goes on. So, why do we care about HCl electrolysis? It's for chlorine production. So, chlorine production is a surprisingly large industry, and there's a few main ways that we produce chlorine on the scale that it's needed. The original was the Deacon process. Deacon process is the reaction of oxygen with hydrogen chloride over a supported catalyst. Originally, it was copper chloride. These days, you typically have either chromium-based or ruthenium oxide-based catalysts, and the temperature required is about 400 to 450 degrees Celsius. It works very nicely. You get chlorine and water, and then you do a little post-processing to separate the chlorine from the water. But it is, as you might imagine, very energy intensive. So the main way these days that you actually get chlorine is actually from electrolysis of brine solution. And it's exactly what it sounds like. You have a sodium chloride solution that comes in, a semi-permeable membrane that separates the two, and you generate your chlorine gas on one side, you generate hydrogen gas on the other side, and what you're left with is what is sometimes called caustic ash, or basically sodium hydroxide. And then whatever residual brine is unreacted. The other way that's picking up some steam is actually membrane electrolysis. In this case, it is aqueous HCl on the anode and then oxygen on the cathode. And so you end up with an oxygen depolarized electrode. And the reason you do this is by using an ODE, you reduce the cell voltage that's required. So BASF and De Nora actually have a developed commercialized system that they use. And so they can generate about half an amp per square centimeter at 1.3 volts. So because of this ODE, they can actually bring the required voltage way down. The brine process, by comparison, typically runs closer to 2 volts. So it's a little bit more energy intensive. And so, anything that brings the cell voltage down is generally going to be a bonus. The membrane electrolysis here runs at about 26% conversion efficiency on a single pass conversion. And the main issues here are that you have to do sort of pre-processing and post-processing steps. So you have to make sure your water content is an appropriate amount. So there's a range of HCl concentration that works for this system. And then after you produce your chlorine gas, you have to separate it from the unreacted HCl and the water. You typically need a relatively dry chlorine stream. There are also some limitations that occur due to formation of hydrogen on the anode or on the cathode, and that transfers over to the anode. So you have to be careful that you don't end up with too much hydrogen in here. Similarly, you have to be careful that you don't have oxygen crossing from the cathode to the anode, because you don't want to have a high concentration of oxygen in the presence of chlorine, potentially have some bad reactions. So more recently, within, let's say, the last 20 years or so, there's been a push to try and do a gas phase version of this membrane electrolysis. And there's a couple of big reasons for that. Anytime you can operate in the gas phase, especially for a chemical reaction, you vastly increase your rate of reaction because you vastly increase the rate of diffusion of your reactants. And it could be as little as 10 to the third faster, but it can be up to as high as like 10 to the 5, 10 to the 6 times faster. So you're talking about literal orders of magnitude greater diffusion surface. So if your catalyst is good and you can get very high turnover, you effectively are only limited by how quickly you can get your reaction to the surface. So if you can do it faster, you can get more turnover, you get better throughput. Everything works better. You typically get lower energy costs as well. And as you might imagine, if you can operate in the gas phase, might have easier separations and things like that, depending on what your reactants are. But the reason this is of interest is, like I said, chlorine is a surprisingly large business. I honestly didn't have any idea that it was quite this big. But in 2021, there were about 92.3 million metric tons of chlorine produced, and it had a market value of about 35.7 billion dollars. So it is a big business, and so anything that you could do to make it more economically viable, that's a big deal. So that's what we're trying to do. But the gas phase process, like I said, it's been worked on for about 20 years, and by large companies, not just at a lab scale, but DuPont and De Nora, again about 20 years ago, tried to make this gas phase process work. But you don't actually see any commercial gas phase processes. There's a reason for that. So DuPont and De Nora's attempt was basically anhydrous HCl on the anode, and a dilute HCl stream on the cathode. And they actually did develop a commercial prototype of their electrolyzer. This wasn't some sort of general idea that they kind of tried out real quick and gave up on. It was a years long process. The proof of concept was actually originally shown at UC Berkeley in 1993. DuPont made a 300 square centimeter model in 94. Like I said, it had anhydrous HCl on the anode, dilute HCl on the cathode. And they actually made it work. They got 1.3 amps per square centimeter at 2 volts. That was in the first generation. And then in 1994, they developed a 2 square meter model that could get about 1.2 amps per square centimeter, but at 1.7 volts. So they brought the cell voltage down in the second generation, and that's actually what this image is over here. Is the second generation electrolyzer. So that's 3 cells, each of them being 2 square meters. So it's a very large electrolyzer, and that it worked. And they were able to get the current efficiency greater than 99%. DuPont's second generation, one of the next steps that they took after sort of getting the scale up done was to move to catalyst coated membranes. And this was around 1997, 1998. And the actual electrolysis itself worked. So why did it fail? Like I said, you don't see any of these as commercial processes. There's a reason for that. So these are basically the limitations on gas phase HCl electrolysis, at least as DuPont De Nora implemented it. Anhydrous HCl will react very readily with water. There was an old chemistry textbook when I was an undergraduate, and I believe it said that about 400 volumes worth of HCl will react with a single equivalent volume of water. So it reacts very, very readily, and that's an issue because what it means is that if you have water anywhere in your system, even if you try and keep it on one side, water is eventually going to cross from the cathode to the anode, and as soon as that happens, that gas phase HCl becomes liquid phase. So you run into that issue of liquid phase diffusion, just gas phase diffusion. Everything slows down. The other issue, of course, is you do have this post-electrolysis separation of H2O that needs to happen to get your chlorine in a dry state. And so that's an extra post-processing step. That's extra energy, extra money that has to go into equipment. And so it increases the capital and operating costs that are associated with it. More importantly, is corrosion. So corrosion was actually the main issue that DuPont went into. And specifically what was happening was oxygen radicals that were forming from water that crossed from the cathode to the anode would consume the carbon supports. So you would basically end up with this reaction of a carbon with 2 oxygen radicals forming CO2 and just destroying the catalyst support. And so, as that happened, the system would break down, and it didn't even last a year, which on an industrial scale is a big problem. Cost that's associated with putting these together, with the catalyst costs that are associated with it. You need this system to last for 5 years, 8 years, 10 years ideally. So the fact that it was breaking down after a year or so, or not even quite a year, was a big problem. It was ultimately one of the main issues, or one of the main reasons that they didn't pursue this any further. And then, of course, although the current efficiency was greater than 99%, they did have to be careful because when you have water in the system, you do have the possibility of the water crossing over and getting oxidized and basically being a parasitic side reaction. And if it does form, you also will have oxygen in your anode stream, and that's also a problem because that's another separation step that you have to take if the oxygen concentration is high enough, or if whatever subsequent reaction you're hoping to use chlorine for can't have oxygen present. So all of these things were sort of the part and parcel for why this process never really got off the ground. But because of all the potential benefits of operating the gas phase, I wanted to revisit it. And the reason we were able to do so was this, polybenzimidazole membranes. So all of the original work had been done with Nafion membranes. And if you've ever worked with Nafion, you know that one of the main rules of Nafion is it must have external hydration. Proton conductivity will absolutely tank. And so that's why in the DuPont De Nora system, they needed that HCl stream because they needed to have some amount of water going on the cathode to go into the membrane and provide the hydration that was necessary. But we have these polybenzimidazole membranes. I'm going to give a very brief overview of the synthesis. If you were interested in the details of the synthesis, I would very much encourage you to go read the 2005 paper from the Benzowitz group. Brian Benzowitz is actually at Carolina. His group is the one that made all of the membranes that are in this paper, in this talk. So I will sort of go through, like I said, the very brief synthesis of it. But if you're interested in these membranes, please check out these papers. They're very cool. It's really great work. There's all kinds of different variations on it that have different properties, and they're doing a lot of really cool stuff with it. So the synthesis originally was you take polybenzimidazole, you grind it up in a DMAC, and then you heat it up, and then you cast it, and you have to do a subsequent doping with phosphoric acid, and it worked, but not very well. And so the big innovation that Dr. Benzowitz's group came up with was what they call the polyphosphoric acid method of synthesis. And so what they take this tetraamino biphenyl and then isophthalic acid, mix them together in polyphosphoric acid, do the reaction at about 190 to 220 degrees Celsius, and then they can cast the film directly. And as the polyphosphoric acid hydrolyzes, you get the polybenzimidazole membrane with the phosphoric acid dopant built in. And that seems like a very simple thing, but what it effectively did was roughly triple the amount of dopant that could go into the membrane. And what that resulted in was a simpler process that could be repeated very easily, but it also gave significantly higher conductivity than any previous PBI membrane had ever shown before. So there's a few different membranes here. The diamonds are Nafion. So you can see that Nafion above 100 degrees Celsius, or even at 100 degrees Celsius, its conductivity basically goes away because you were boiling off all the water. It does not work very well. All of these traces down here, so the open squares, closed and closed triangles, are different conventionally made PBI membranes. So what we would call the conventionally imbibed method. So you make the PBI membrane, then you soak it in phosphoric acid, it uptakes some of that acid, and that acid acts as the dopant that conducts protons. This circle was the conventionally made, sort of the best one that the Benzowitz group could make by the conventional method. And then these closed circles are the new polyphosphoric acid method. So you can see that, especially above 100 degrees Celsius, the conductivity is, anywhere from 5 to 10 times higher than any of the other comparable membranes. And so that's a really key thing. So the first benefit of using polybenzimidazole is you have conductivity that's very high at temperature above 100 degrees Celsius. That already opens up a lot of possibilities that Nafion has previously precluded. Second thing is PBI is very, very stable. This is a different paper, so this would be the 2019 paper. It shows extremely high stability. They've done multiple versions of this multi-year operation. This one in particular was a high temperature proton exchange membrane fuel cell. It ran for more than 2 years and would actually have continued running for more than 2 years, but the building had a power failure, so the hydrogen tanks shut off as a safety feature, and then the cell shut down. Um, it really works exceedingly well. Over the course of this 2 years, they demonstrated a loss of cell potential at a fixed current density of only 0.6 microvolts per hour. And so what that means is basically the membrane was pristine. All the loss of cell potential was due to uh, catalyst activity loss over time, which is really incredible. So again, you get very high chemical conductivity, very high physical stability, and you also get really good, strong acid tolerance. So historically, we knew that at least up to about 8.5 molar sulfuric acid, the one of the variations of the PBI showed just rock solid conductivity, or if you prefer to think of it as area specific resistance. And what that means is, regardless of the acid concentration, at least in this range, the proton conductivity of the PBI membrane was unaffected. And so that's a really important thing when you want to work with 100% HCl. But we didn't know for sure if that would actually be true. Again, this is 8.5 molar sulfuric acid, not pure sulfuric acid. So let's talk also about the catalyst synthesis. So when we started this project, we dug into the literature, looking for a chlorine evolution reaction catalyst that would be potentially good. We weren't really looking for the absolute best. We just wanted something that would work reasonably well and be pretty stable. And digging into the papers, we found that iridium ruthenium oxide showed up a lot. So we used a pretty just standard solid state reaction. Mix iridium chloride, ruthenium chloride, and sodium nitrite together in a crucible with about 10 milliliters for IPA. Sort of grind it all together just to get it well mixed, and then anneal it at 500 degrees C for 2 hours. That boils off the IPA. You end up with a solid state reaction. The materials mixed together, and what you end up with is a mixed metal oxide. But it does have some contaminants in it, including this leftover sodium nitrite. So you wash it with water multiple times, centrifuge powder down. But then the key step here is you need to do a reaction with 0.1 molar perchloric acid at 80 degrees C for about an hour. And that gets rid of any residual sodium nitrite that the water didn't get rid of. And it is actually noticeable through XRD. So before and after doing this perchloric acid step, peaks that pertain to sodium nitrite disappear after the perchloric acid step. And, it didn't seem to make a difference in terms of the actual reactivity, but, when you want to make sure that you have as much reproducibility as possible, that's really important to get rid of all those contaminants. And so initially what we did to check the catalyst activity was just some rotating disc electrode experiments at different acid concentrations of HCl. And so you can see here, this is all iridium ruthenium oxide, 1 molar to 9 molar. You can see that the concentration of the acid gets higher, the activity goes up, it works very nicely. It cuts off here at 500 milliamps per square centimeter because that's actually the limit of the potency stat that was connected to that. So we don't know what the limiting current looks like on these, but what we were mainly looking for was just the high activity. So that's the key thing. It works well. So it looks like it's a good catalyst. Again, the literature says it's reasonably stable. Great. We don't have to worry about it anymore. We're good. This is the MEA preparation. So I'm not going to go through every single bit here, but I wanted to compare it with the Nafion membrane, the MEA preparation. So Nafion MEAs, pretty much you could take your gas diffusion layers, put them on either side of the Nafion membrane, and hot press it, and you're done. That is not the case with PBI. PBI does require a little bit more of the kid gloves, but it is still a relatively simple process. You have to take a little bit more care with it. The Nafion, the PBI MEA uses these Kapton subgaskets. So we attach those to the GDEs first, so the gas diffusion layers with the catalyst sprayed on them. And we attach the subgasket, you press that first, and so you end up with your two sort of subgasketed electrodes. So you have your anode and your cathode, and then you put your PBI membrane between those two, press it again with some shimming to ensure that the compression is controlled. to be about 75 to 80% of your initial thickness, and you end up with this really, honestly, very photogenic MEA. It really looks nice, and it is, interestingly enough, something that you can handle with your bare hands. You don't, it doesn't do anything to you, which is honestly, it's really pretty cool. It's a nice material to work with, especially once it's been pressed. It works really well. So I'm going to talk about the experimental setup and some of the safety features that go into this. As you might imagine, anhydrous HCl is a pretty nasty substance. And we had to do a lot of things to try and make sure that it was safe for us to work with. So a couple of things. This is just a very general schematic. The main thing here is we had a pump purge system that would remove the moisture. And before we were going to do any experiments, we would do a minimum of 10 to 15 cycles. So typically the day before, we would run this pump purge cycling, bring the whole system up to the flow meters down to about 2 millitorr, and then we would refill with nitrogen, and then do that repeatedly. The main thing that we tried to do was not have HCl go through the vacuum. That's mean. And so what we would do is whenever we finished experiments, we would run nitrogen through the whole system while the cell cooled down. And so we would try and get as much of the HCl out as possible. And so when we weren't using the cell, it's not shown here, but we had some cutoff valves before and after cell hardware when it's hooked up. And so when we're done, we pump the dry nitrogen into the whole system. So everything up to the regulator on the HCl tank, all through the rest of the system, not including the vacuum, we keep it under a positive pressure. And in doing so, we minimize the possibility of water getting into the system. And then in addition to that, we also heat the electrolyzer at 120 degrees C for 3 hours under nitrogen flow before we would run any experiments at all. And so the goal there was we drive off as much water as is going to come, that's going to come off as possible. And in doing so, by running both of these things together, we basically push all the moisture out of the system, whether we pull it out through the vacuum or we boil it off through heating the electrolyzer. We try and get all the moisture out of the system that we can. And we know it worked well because we don't see corrosion inside our pipes. When we take the cell off, for instance, we don't see corrosion at the junctions. So we know that we're doing that correct. And, like I said, if we did have liquid in the system, we would not see HCl flow through when we turn it on. We do actually get bubbles that form, at least initially, in the solution. Speaking of the solution, it's saturated potassium hydroxide, aqueous solution of it. We run both the anode and the cathode outlets through that, just in case some HCl crosses over or something like that. We had the solution stirring at all times. It is, when I say saturated, I mean there's a pile of potassium hydroxide pellets sitting in there. And we also do pH testing consistently. So when we were running experiments, we would do it on about an hourly basis, not while the HCl itself was flowing through. We would typically do it while we were changing the temperature. So there was nitrogen running, but we would check that pH. If the pH was anything less than 14, we would immediately add additional potassium hydroxide, stir the solution, and then check the pH again in about 10 minutes and make sure that it was actually 14. The reason we stirred the solution was to make sure that we didn't end up with any sort of hotspots, so localized areas where the pH had risen or gone more acidic, I guess. And that way we ensured that any HCl that was unreacted that made it through the system would react with the potassium hydroxide and form, water and salt. In addition, the chlorine would go through it and also typically react with the base. And then, of course, the hydrogen is not as big of a deal, but what we wanted to do was bubble it through water to ensure that there wasn't any buildup of hydrogen gas. And although it's unlikely, we want to eliminate the possibility of an autocatalytic reaction or something like that and cause an explosion. Finally, the last thing that we did was when we switched from nitrogen to HCl, we allowed the pressure of the system to drop to close to atmospheric before we switched from the nitrogen to the HCl. And all that was to do was to prevent overpressurization of this regulator here. Um, again, we never had an issue with it because we took those precautions, but we typically kept the pressure of the system to about 30 psi, at least based on this regulator. So I think that's most of the safety checks that we did. If you do have any additional questions about them, I'm happy to either answer them here or send me an email or something like that. We absolutely want to encourage safety. If you're going to mess around with anhydrous HCl. Yeah, and so this dashed red line is basically where the pump purge operated. So it covered everything up to the flow meters that we used. That we the goal was to keep moisture out of this system, out of this piping system prior to the electrolyte. We used the heating and nitrogen flow to drive it out the back, and then we kept positive pressure on the system to prevent any backflow as well. So, how well does the PBI actually stand up to 100% HCl? As it turned out, really, really well. The conductivity at 160 degrees Celsius is about 5 Siemens per meter. And to put that in context, the conductivity of the PBI that I showed you previously was about 25 Siemens per meter. So, in a hydrogen air fuel cell, the conductivity was only about 5 or 6 times higher than what we observed, which is fantastic. And you see that the trend of the area specific resistance also matches what we saw previously. So if you want to mentally invert this, it gives you a rough idea of what the conductivity looks like. So basically what it means is that as the temperature increases, the conductivity of the PBI membrane also increases up to, again, about 5 Siemens per meter. And we determine these membrane resistances from the high frequency intercept of our electrochemical impedance spectroscopy measurement. And in this case, the membrane active area is about 10 square centimeters. And so you can see, especially as we get to higher temperatures, the resistance measurements tighten up as well. So we're reasonably confident that we are actually measuring membrane resistances that are accurate. And so this is great. It means that the PBI is retaining high proton conductivity even in a completely water-free environment. That's a significant thing because if you recall, one of the main issues that Nafion has is that it cannot operate in a completely water-free environment, or at least not for long. So we are able to do that. How about crossover? Crossover could potentially be a big issue. It doesn't matter how good your membrane is if you have major crossover of chloride. That chloride in particular is really good at poisoning catalysts, especially something like platinum, which is really, really nice to use when you're trying to do hydrogen evolution. Fortunately, what we found is that the crossover was very low. The way we measured it was similar to hydrogen crossover in a fuel cell. We set the cathode as the working electrode, applied an oxidizing potential under nitrogen, let the cell get to a steady state, very low current, and then we would flow HCl on the anode and look for a current increase. So what we assumed was that any current increase was the HCl crossing over from the anode to the cathode, and we also assumed that based on the potential that we chose, 100% of the HCl crossing over was immediately oxidized. So all of that current increase was due to HCl, and so we could back out what the molar crossover rate was. And so, look, we normalized by the area of the active area of the membrane, and so we know roughly what the chloride flux was, and so we're able to go back into literature and compare it with some of the other results. And what we find is that even though we're using 100% HCl in the gas phase, our crossover rate is actually as low as or lower than basically every other membrane that I was able to find a number for. Even when the concentration of chloride was very low, in this case 10 millimolar, and even as you get to much higher ones, so like the most comparable anhydrous HCl system, the one that used the HCl with the ODE in the gas phase, the calculated value they used sort of a theoretical value here was almost 2 orders of magnitude higher. So all this is to say, crossover is very low, conductivity is very high. This is looking good. So polarization results, sort of the ultimate goal here is, can you actually do this reaction? And as it turns out, you can. It proceeds really nicely, and as temperature increases, the reactivity increases. So you can see here at 30 degrees Celsius, it's pretty bad. But as you go to 50, 100, 120, 140, 160, you get significantly better activity. And in this particular curve here, uh, the point here at 160 degrees Celsius and 1.8 volts is about half an amp per square centimeter. And as I'll go through in a minute, that actually works out to, based on our calculated molar flow rate of HCl, about 100% conversion efficiency. So even though we're operating in pure acid, no water, we're able to make this reaction not only happen, but happen very efficiently. So all of this is on a per single pass efficiency calculation, and it works really well. And so what we see, again, increasing current density with increasing electrolyzer temperature, which is good. That means that we're able to make the reaction proceed more readily. Current conversion up to 100% based on the calculated molar flow of HCl, and I'll go through that in a minute. And what we see is that above this equilibrium potential of about 0.96 volts, which is for gas phase oxidation of HCl, the liquid phase is about 1.36. The polarization response is largely linear. And what that suggests to us is that there's no real mass transfer limitations. It may also suggest that this is not actually 100% conversion efficiency, because you would expect that to starve the cell. But it does mean that we're seeing very, very facile reaction, and we're not limited by getting the reactants to the surface. That's the big plus of the gas phase reaction, is that you get much better diffusion to the surface. So how do we determine this efficiency? Ideally, we would run this experiment. We would send the gas outlet stream through GCMS. We would actually quantify how much chlorine was made, and then we would compare that with the total charge that was passed, and be able to say exactly what the conversion efficiency was. We don't have a GCMS, and even if we did, I can't imagine that running pure acid through it is a great idea. So what we did was run the experiment. We did some qualitative noticing of changes in the bubbles that happen between nitrogen, HCl, and chlorine. Specifically, nitrogen, no surprise, just gives very regular bubbling. HCl actually doesn't give pretty much any bubble at all, because as soon as the HCl hits that basic solution, it immediately reacts and forms the water and the potassium chloride salt. But when we turned the voltage on and we were actually oxidizing the HCl, we started to see bubbles again. And that was the formation of chlorine. And so what we saw were larger bubbles compared to the nitrogen, but also slower bubbles. So sort of the chlorine hitting the basic solution, not reacting as readily as the HCl, but still eventually reacting. So you would see these kind of large bubbles come out of the end of the tube, go into the water, and then sort of dissipate. But what we could do was calculate the expected molar flow rate based on cell temperature, pressure, and the volumetric flow rate. I used a program called DWSim. It's basically an open source free version of Aspen. And so, I did check the numbers against an actual Aspen version. They did match. So we used that to calculate the molar flow rate for all the different temperature conditions. We actually measured the pressure using the nitrogen flow immediately before the cell, so we knew what the pressure was based on any pressure drop that happened through the flow meter. And then we could compare all of that with the total charge that passed at a given voltage. So we knew what the current density was at a given voltage, and so we could back out what the conversion of HCl to chlorine was, assuming the 100% Faraday efficiency. We make the argument that that's a reasonable assumption. There's no water in the system that acts as a parasitic reaction. And when we use nitrogen only, we see basically we saw a current below the limit of our power supply, less than 0.0001 amps per square centimeter. So no background current to speak of, no side reactions that should be happening. So we think, assuming basically 100% efficiency is reasonable. So what are the major conclusions? The first one is that we can actually split anhydrous HCl efficiently with water present. That's a big deal. PBI membranes maintain proton conductivity under even the harshest conditions. So in this case, again, completely dry system, 100% anhydrous HCl. It worked flawlessly. Higher electrolyzer temperatures do increase conversion efficiency. If you're a chemist, you know that most reactions proceed more quickly at higher temperatures. And we were glad to see that in this case, the same was true. And what we're hoping that means is that we are reducing the anodic overpotential of the reaction, which means that we're lowering the overall energy that's required to make this thing go. So you're not going to operate these electrolyzers at 100% conversion because that means you're starving the cell. But if you're operating at say 50% conversion, you want to run that at the lowest voltage possible. And so by increasing the temperature, which is it sounds like it's more energy intensive, but in practical terms, in an industry setting, heat is readily available. So you use some good insulation, you can keep the cell maintained at 160 or 180 degrees Celsius, no problem. And that brings your cell voltage down significantly, which increases energy efficiency, your operating costs, and everything else. The other big thing here is that more work needs to be done to increase the throughput. So we ran everything at 0.1 liters per minute. When we tried to increase the voltage or the volumetric flow rate after we had sort of established the general process, what we found is that we didn't actually see any increase in the current density. And so what that suggests is that is the way our system was set up, increasing the flow did not actually increase the rate of reaction, which suggests that the HCl at higher flow rates was basically just moving through the system without doing anything. And so what that suggests is that we're going to need to come up with a way to keep that in the system longer, and I'll talk about some of that in work. The first thing is we want to see if we can find some thinner membrane. And as it turns out, Dr. Benzimidazole's group is working on that. They actually have a specified PB that may fill this role. The reason we want a thinner membrane is that a thinner membrane should give you lower ohmic. Since we didn't see any mass transfer limitations, the next thing that was dominating was the ohmic losses, as evidenced by the straight line that was formed. And so what we want to try and do is decrease that resistance due to ohmic losses, and traditionally a thinner membrane manages that. It makes it easier for protons to cross over. The potential for chloride crossover happening at an increased rate is a potential issue. But some of our initial measurements there have suggested that the crossover rate is actually not significantly higher even for a thinner membrane. So hopefully we kind of get the best of both worlds. We keep our crossover of fluoride low, but we get better, get lower ohmic. Catalyst improvement is also a big thing. So we used iridium ruthenium oxide. We used it at a loading of 3 milligrams per square centimeter. Iridium and ruthenium are both very expensive, and so it'd be nice if we could either and reduce the loading, maintain our catalytic activity, or ideally find something that's cheaper. So in using fuel cells as an example, platinum works obviously very, very well, but platinum is also expensive, and so there's been just decades of work into reducing the amount of platinum that's necessary to achieve the same catalytic activity, whether it's through substitution of platinum for cobalt or something like that, or generating smaller, stable platinum nanoparticles so you can use less platinum and still get very high surface area. There's a lot of work there, and the same thing probably needs to happen here. Iridium ruthenium oxide will work well, but that is going to be pricey. So find a cheaper catalyst that still works well and still stable. That's really the ideal. So going back to the flow rate increase, where we didn't see any additional current density, which indicated no additional catalytic reaction, we want to try using back pressure. So in a fuel cell, back pressure gives a longer time for reaction, and so it lets you run at higher flow rates and generate higher turnover. And so we suspect that we could do the same thing in this electrolyzer. We apply some back pressure, which effectively increases the pressure inside the cell, and that should let us use these higher flow rates, get higher throughput, and still maintain good activity. And so when we do something like that, we may actually find where the mass transfer limitation region is, which would be useful to know as well. because that'll give us some idea of the maximum throughput that we can generate, and what a good conversion efficiency to run at, whether it's 50%, 75%, something like that. This is how we'll kind of figure that out. And finally, the last thing that we want to do is look at catalyst-coated membranes. So all the work in this experiment, or this project, was done with catalyst sprayed on the gas diffusion electrodes, and that works very well. But if you can spray your catalyst directly onto the membrane, you pretty much always will improve performance because you're going to reduce the transport length for the protons. And by doing that, you significantly reduce your ohmic losses. And so, in general, catalyst-coated membranes are the state of the art, fuel cells or anything else. And so we feel like that's one of our next steps as well, is trying to work out the best way to do this ink spraying straight onto PPI membrane. As far as I know, nobody else has done this, and so we'd like to try and figure it out. So I will finish by acknowledging everybody that worked on this project. So we have our student researchers, Chris Lickett-Honorak, Rimbert White, and Dr. Laura Murdoch. Chris and Rimbert worked with me on the experimental side, and Dr. Laura Murdoch is the one that made all the membranes that we used in our work. She is a polymer expert, and she just recently defended her dissertation. Rimbert is actually at UC Santa Barbara, so he was not an undergraduate. He had just graduated, and it happened right at the start of COVID. Didn't get to visit any schools, so he actually ended up working with us for about a year and change. He did a lot of fantastic work. We're very grateful to have him work in the lab. Chris is coming up on his roughly last year of his PhD. Did a lot of, again, a lot of great work. We also collaborated with Dr. Siravash Shipali and Dr. Brian Benzowitz. So Dr. Benzowitz was Dr. Murdoch's mentor. Brian is the one who developed the original PPA process that I showed you at the beginning. He is an internationally recognized expert on polymers, and of course, in particular, imidazole polymers. He's got his hand in a lot of different things. It's really great working with him. Dr. Shimpali is a research professor here at University of South Carolina. He's the director of the Hydrogen and Fuel Cell Center, and he is a theory whiz. Need anything modeled, electrolyzers, fuel cells, batteries, you name it, he's the guy to talk to. So he provided a lot of input, design of experiments. He is also working to help do some of the modeling of the HCl electrolyzer so that we can better understand what's happening inside. So where's the cell being starved? What potential conditions might optimize the operation, things like that will help us plan for the next round of experimental. And then finally, I need to thank our funding source, which was BASF. BASF is interested in applications, in this case, the HCl process. So with that, I will say thank you to everybody for watching. Any questions that you asked? All right. So let's see. So any questions that come in, keep them coming. That's fine. Is it common for larger cells to be more efficient in terms of the voltage that's necessary? It's possible, but they actually tend to be a little bit less efficient in terms of the voltage that's necessary because you run into issues with mass transport through the system. So the larger the cell is, the less homogeneous the transfer of reactants is. And that's actually one of the places that modeling comes in handy, especially is as you try and scale up from, say, like our 10 square centimeter cell to, let's say, to make it simple and say a meter squared. One of the things that you can do is take a model of the 1 meter squared cell and then figure out how best to plan for the flow paths basically of the cell. So for instance, in fuel cells, You might think that, intuitively you might think, oh, okay, I want to have as many serpentine paths as I can. That gives me the maximum amount of reaction area. But it turns out that that's not the case. So up to a point, yeah, you want to increase the number of serpentine pathways. That does actually help you out. But if you go too far, your channels get too narrow, and you actually end up hindering the flow of your gas, which actually hurts your cell. So all of that's to say, larger cells can be more efficient, but generally they actually are a little bit less efficient because of some of the some of the issues that come up just from scaling the entire electrolyzer. But there's a lot of engineering work that goes into it, and so sometimes there are ways to get around that. So you can have like, in our case, our cell is so small that it only has a single inlet on each side. But if you have, a large uh, cell hardware face, you could put multiple inlets there, and so you would effectively overcome the limitation of flow by providing more places for the gas to come into the cell. Similarly, more places for it to come out as well. That's a great question. Let's see. Is it possible to use first row transition metals for these cells? Are they too unstable? That's a great question, and the answer is I don't know. Ideally, it would be nice to find something that's cheaper than the platinum group metals. Um, but it's something that we could check relatively easily by using like rotating disc electrodes. So we could put it into an acid solution. It would be aqueous, so not exactly the same, but it would give us at least some idea of the stability over time. So we could just run, cyclic voltammetry back and forth and see if the catalyst activity dropped off over time. But that would definitely be something to look at to see if there's any possibilities there. Let's see. So for the reaction setup, how do you prevent the water vapor from the aqueous KOH from interacting with the cell? That's a good question as well. So one of the ways that we do it, we don't have any specific mechanism like a check valve or anything, but what we do is twofold. One, the aqueous KOH is set. The tubing from the end of the cell to the KOH is long, and we also always have some amount of gas flow happening. So the pressure is always pushing out from the cell, from the electrolyzer, towards the aqueous KOH. Additionally, the cell is always hotter. At least during experiments, the cell is always hotter than the KOH as well. So it should prevent any sort of reverse pressure buildup. When we actually shut everything down, we have shut off valves, so we can actually close off the outlets of the electrolyzer from everything. If we wanted to, we could close off the inlets of the electrolyzer. Typically, what we'll do is close off the outlets of the electrolyzer. Then we put nitrogen into the system on both sides, and we build it up to a pressure of like 30 to 40 psi gauge, and then we close the inlets from the nitrogen as well. So what we do is we try and seal from the everything from the nitrogen inlet to the hood all the way to the outlets of the electrolyzer. We keep all of that under a positive nitrogen pressure to try and prevent the incursion of water vapor. But like I said, if we let that system sit for like a week, then what we will do is that pump purge cycling to try and get the water out prior to the electrolyzer, and then before we actually run the electrolyzer, before we put any HCl in there, we'll keep it at 120 degrees Celsius, also under nitrogen flow, for at least 3 hours. And so, the idea there is that we can pretty much boil off and blow away any water vapor that's in the system. But that was the water vapor was a huge concern for us because, like I said, if you have anywhere in your system, that HCl is going to react immediately with it, corrosive puddle, and start eating away. But we were actually able to use stainless steel throughout our entire system, pretty much. Some of the piping was PTFE, but we used stainless steel swage lock connections and things like that, and we've had no issue with leaks. We did a helium leak test before we ran anything. So we had some issues with leaks, and we used the helium leak testing to find out where those leaks were. Turns out it was actually at the HCl bottle. The regulator connection was not tight enough. But once we tightened that up, we could go through the entire thing from the HCl bottle all the way through the electrolyzer, check each joint with the helium, and see that there was nothing coming out, which was great. That was how we finally got some confidence that we had everything sealed up. So that's sort of the gold standard. And I need to thank, there's a guy, his name's Richard Douglas. He runs the company. He actually installed the sensors that are in our hoods to detect if there is like an HCl leak or something like that. And he was the one that told us about using the helium leak detection as sort of the best possible way to determine if you actually had any leaks anywhere in the system. So that was how we ended up doing it. And again, if somebody's watching this and they're curious about the procedure for that, absolutely, please reach out and get in touch. We are always happy to help people with that, because it was a big headache, but it did work really, really well once we had it sorted out. Let's see. Could you flow a certain amount of reaction gas through a solution with a known amount of something that reacts with chlorine and then titrate to see how much was created? That would be ideal. And I did look in the literature for some of those, but the problem is that pretty much all of the methods that I found were looking at dilute amounts of chlorine. And so what we were concerned about was that we would effectively be underestimating the amount of chlorine that was produced. Um, but yeah, we would like to accurately quantify how much chlorine is being produced. And like I said, GCMS would be the ideal, but we also don't want to run HCl in there and just obliterate everything inside because it is a very sensitive system. So we're still trying to think of a way to do this. But yes, that's a really good question, and it is what we would like to do. So if anybody knows a good way to do something like that, please let us know. We absolutely would like to do that, to really be able to be certain about reaction or how much chlorine we're producing, what the conversion efficiency is. But for the time being, we were settled for the qualitative answer for that one. But I think that's all the questions we have. So I will say thank you to everybody for coming out. The paper will hopefully be out soon. We'll see. Blow chlorine through an alkene, through the reaction with chlorine, and then idea. Now, that's an interesting idea. Do the alkenes generally, like, could we count on the alkene reacting completely, such that we could, if however much alkene there is, or however much chlorinated alkene there is, we could say that backs out to like 100% conversion of the chlorine with the alkene. That's an interesting. Yeah, that makes sense. Yeah, chlorine is pretty good at chlorinating stuff. That's very true. Yeah, that's an interesting idea. That might be a cool way to get at it. I'll have to look into that. That's Yeah, that's a good idea, Ross. Um, yeah, that's interesting. Tracer are quite activated and will react very well with chlorine. All right, I'll have to dig into that. That's a really good idea, because that's something that would work really well, because we could bubble the chlorine, the reacted chlorine, or the chlorine that's formed through that. But yeah, that'd be great. Yeah, let's talk about that. That's an interesting idea. So thank you to everybody for coming out. I really appreciate it. Thank you for listening to the talk. It will be uploaded to YouTube in a little bit. So if you did miss any of it, please feel free to check it out there. Meantime, thank you to everybody for coming out. We'll be back next week, I believe. Let me double check and make sure. Yeah, we'll be back next week. We have Sarah Kearney from the University of Florida. And then the week after that is July 15th with Science Palooza 2022 with those 11 talks that I mentioned before. But I hope you will come out for that as well. And meantime, have a great weekend. Have a fun July 4th. Be careful with the fireworks if you're using them. And I will see you all next time. Thanks for coming out, everybody. Have a great weekend.